This is the Building Automation Monthly Podcast with Phil Zito, episode 188. Hey folks, Phil Zito here, and welcome to episode 188 of the Building Automation Monthly Podcast. And in this episode, we will be talking about chilled water systems. So we're continuing our series on HVAC control, and we've got about 2 more episodes left. I think we're going to get through all the chilled water systems in this episode, but we shall see. So in this episode, we're going to talk about what chilled water systems are, how they work, how they function. We'll look at air-cooled water, cooled. We'll look at cooling towers. We'll look at partial load chillers. We'll look at lead lag, all the fun stuff. So this episode is sponsored by our Control Sequence Fundamentals course. If you are looking to learn how to control HVAC systems with your building automation system, and you're like, man, I really know I need to know HVAC, I need to know how to think about systems, I really need to understand all of that, but I have no desire to become a mechanic, I have no desire to go to trade school, I simply want the quickest way possible to learn exactly what I need to know about HVAC in order to succeed with my building automation career, then Control Sequence Fundamentals is for you. This completely online course will teach you everything you need to know about HVAC in order to be successful as a building automation professional. And you can find out more about the course by going to buildingautomationmonthly.com/188. Once again, that's buildingautomationmonthly.com/188. All right, so chilled water systems. So in last week's episode, we talked about hot water systems. And in that episode, our primary focus was using some form of heat generation to transfer BTUs into the water stream so that the water could deliver those BTUs to the airstream within the building. Now, flip that with chilled water systems, we're looking at removing BTUs from the airstream from the building. And we'll talk through how we do that both with air-cooled chillers as well as with water-cooled chillers. So you may be asking yourself, what do I need to know? What is new with chilled water systems? Well, first off, there's some new terminology that we need to understand. And those are things like condenser side versus evaporator side. I kind of stumbled on that word there for a second. Load versus lift, tonnage, and full load amps. These are all terms that you will hear utilized quite a bit as you work on chilled water systems, both in the sequencing as well as when you're working with mechanics during startup, those kind of things. So you really want to understand these concepts. So we will come back to those as we move through this episode, so don't worry about that. Now, I've got some good news. What we covered in our hot water podcast, it really applies to chilled water as well, largely. Now, you may be thinking to yourself, Phil, how does heat relate to chillers and adding heat and all these things? And I'd be like, well, think about it. We're adding heat to hot water and then transferring that heat into a building. With chilled water, we're just doing the same thing, just in reverse. We're taking heat out of the building via chilled water coils that exist in airstreams, typically on return or on mixed air single path units, things like that, and occasionally on outdoor air units where we're actually removing heat from an incoming outdoor airstream. But we're removing heat either before it enters the building or removing it from the building as we recycle the air. And we need to focus in on that concept of heat removal, but we also need to focus in on the refrigeration cycle. And the reason we need to focus in on that is because the refrigeration cycle is how chillers work. I mean, chillers are essentially giant compressors and evaporators using refrigerant to take advantage of different states of liquid to absorb heat and then transfer heat. All right, so the refrigeration cycle. Now, I have talked about this a bit in kind of some of the past podcasts, and it's a little bit difficult to explain via audio because it's really something that graphically it's kind of cool to see and it makes a lot of sense. But then when you try to talk through it on a podcast, with so many of us being visual learners, it's difficult. So there's going to be an image at buildingautomationmonthly.com/188 that you can look at as we talk through this. Now, ideally, you're not driving and looking at a refrigeration cycle drawing and listening to a podcast. That would be bad, so don't do that. But when you get to a place where you could stop, I encourage you to look at this diagram as we talk through this because it will help it make a lot more sense. So essentially what happens is we've got this, and what we're looking at right here is basically a refrigeration cycle for a air handling unit. And you've got this indoor unit, right? And you've got this heat and it's going into it. And it's condensing the refrigerant, and then the refrigerant goes into and I'm really abbreviating this, by the way, so because I'm not going to spend a whole ton of time on this. But it goes into the expansion valve and then goes to the outdoor unit to the evaporator and then goes back into the compressor, okay? So you've got liquid and gas refrigerant. Like I said, I'm not going to get into the specifics of when it's gas, when it's liquid, when it's pressurized, when it's not pressurized. That's not the point of this. What I really want you to take is that on a chiller, there are also two sides of the chiller. You've got the condenser side and you've got the evaporative side, right? So the evaporative side is typically known as the chilled water side of the chiller. And that is where we're chilling, right? Where we're chilling the air. And chilling the water. And then the condenser side is actually where we're removing that heat, right? We're removing that heat. So the evaporator side, we're absorbing heat. And the condenser side is we're removing and transferring that heat outside, okay? Hence why you hear the condenser side of the chilled water system, the cooling towers all on the condenser side, and then the evaporative side is on the chilled water side. So it's important for us to understand this because once we start to learn about lift and we start to learn about the difference between condenser and chilled water and deltas and all that jazz, it will help us really understand why we control our chillers the way we do, how efficiency works, why we may bring on one big chiller and a little chiller or two big chillers, and what we do when we've got low outdoor air, low ambient as it's called, and we're trying to run a cooling tower. All these concepts, you have to understand first that we're utilizing refrigerant and we are transferring from that refrigerant BTUs to another water source. So in the case, right, we have a chilled water source. It is transferring the BTUs to the refrigerant, and then the refrigerant's transferring those BTUs back to the condenser water source, which then goes out to cooling towers, which transfers the BTUs to the ambient air using typically evaporation. All right. So with all of that said, how does this apply to chillers? Well, we kind of just went through it, but what I want you to really understand here, the one thing I want you to take away is that you've got a chilled water side that is absorbing BTUs and you've got a condenser side that is exhausting BTUs. If you really understand that, and then you understand how cooling towers work, because, I mean, not all chillers are air-cooled. Some are water-cooled, which means we use a cooling tower. And we transfer those BTUs via the condenser water to the tower, which then uses the evaporative effect for those BTUs to transfer. If you really get that, then controlling chillers is not too bad. It's not too hard. I mean, there's certain things you need to know. Open the ISO valves, turn on the pumps, understand primary, secondary loops, decouplers, etc., all that stuff. But that can all be figured out. It's not that bad. So I don't want you to get, a lot of folks get really caught up with chilled water systems and they get paralyzed, and I don't want that to happen to you. Alrighty, so let's go in and talk about chillers, and then we will dive through some sequences. So there's two chiller types, right? There's air-cooled chillers, you've heard me briefly mention this, and there's water-cooled chillers. Now, air-cooled chillers, there's actually a condenser coil and some fans, and it just uses the evaporative effect, and it actually removes the heat to the atmosphere directly from the chiller. Now, you can get away with this for some low tonnage chillers, but typically when you get above, what is it, like 150 tons? Something like, don't quote me on this, but it's somewhere around there. When you get above that, you start to not be able to exhaust enough of the heat from that air-cooled chiller, and you really have to start to use water-cooled chillers and cooling towers. The reason why is just the heat removal requirements, and as well as the way in which you process the refrigerant, scroll versus screw versus centrifugal, which also I won't get in. Those have ramifications on the sizing and tonnage. And tonnage is just simply a rating for the BTU removal capability of a chiller. So as I mentioned, air-cooled and water-cooled. Now, air-cooled, what we need to be cognizant of with air-cooled chillers are really two big things. If you've ever walked out to an air-cooled chiller and you've seen it kind of tucked behind a building, southern exposed, where the sun's just beating down on it, and it's wrapped in like a 12-foot fence because they don't want any noise pollution, and that fence has like no ventilation. And then you wonder why that chiller is not operating as efficiently as maybe one that has a chain link fence and is northern exposed. Well, solar gain has significant effects because it will go and heat the machine, it'll heat the ground around the machine, it'll heat the ambient air around the machine, and then you couple that with a tightly non-ventilated fence where there's no airflow, and you've got a recipe for disaster because ambient is going to heat up. I mean, if you've ever been by a fenced-in air-cooled chiller that's southern exposed, you know that they get pretty hot. And so you really want to be cognizant of location. Now, I realize as a BAS professional, there's not too much you can do about the location of an air-cooled chiller. What we can do, however, is we can be cognizant of these effects so that if our chiller is not performing optimally during design day conditions and we get in a room with an engineer, they're yelling at us and they're telling us it's all our fault that somehow our BAS system magically controls the laws of heat transfer, and heat absorption, that you actually understand why that may not be true and how environmental effects could be impacting the performance of that air-cooled chiller. Now, water-cooled chillers work by discharging heat from refrigerant into this thing called condenser water. Now, with condenser water, it's then pumped out to cooling towers, and these cooling towers have fans and they have spray nozzles, and they essentially utilize the effect of drawing air across the surface of the water or using these spray nozzles to basically create a mist and then draw the water through the mist. And that in turn actually creates evaporation. I was going to say evaporative effect and evaporation at the same time. That creates evaporation, which causes a state change, which causes BTUs to be transferred into the airstream. So we need to be cognizant of that. That is one of our main ways of removing heat from buildings with large centrifugal chillers that are water cooled, that are using big cooling towers. When we're looking at this, we're adding some parts though, whereas an air-cooled chiller is primarily a primary pump, an isolation valve, and an air-cooled chiller, an enable command, and a potentially temperature set point. Now, when we're working with water-cooled chillers, we're adding cooling tower fans, cooling towers, we're adding bypass valves, we're adding spray, we're adding VSDs, we're adding heat trace, we're adding sump levels, etc. All these new variables that we need to take into account in our programming. Now, cooling towers, there's primarily kind of two ways. I guess there's three ways that we could remove condenser water. Cooling towers being the main one. And of those cooling towers, the two ways we can do it is we can do flow through, Or we can do flow over. So flow through is, like I just said, the airflow is going to come across the surface of the water as it flows through the tower. Flow over is where you're going to have a valve that's going to open up and allow the water to flow from the top of the tower, either drip down or spray down, etc. Just depends on the structure, and the fan will go and once again use the evaporative effect. And then there's this kind of third option, which is for low ambient conditions, and that is a heat exchanger. And often what you'll do is you will have a plate heat exchanger sitting within a building, and you can either use this for domestic hot water. You can, warm up the domestic hot water with the heat being exhausted off a plate heat exchanger. You can exhaust the plate heat exchanger to a variety of different things like a radiant heat, etc. And you can use this plate heat exchanger as an auxiliary form of heat. This is where you've often heard of like heat pump chillers, things like that. All right, so cooling tower fans, they exist to bring the air through the cooling tower. And then, as I mentioned, bypass valves will allow us to go and utilize flow through the tower or flow over the tower. And then we have this thing called heat trace, which at least up where I live is pretty important. And essentially it's an electrical heat that exists on the condenser piping that's exposed to ambient, and it will keep the piping from freezing in an ideal situation. I wouldn't trust this 100%, but that's its purpose, is to really help as a hedge against freezing. I really want you to note that it's a hedge against freezing. It's not necessarily going to keep things from freezing. Now, we're going to talk about a couple more concepts here. One is lift. Now, lift is the difference between condenser refrigerant pressure and evaporator refrigerant pressure. And you may be like wondering, why does this matter? Well, in an ideal world, right, the lower the lift, the less the compressor has to work, because the compressor compresses, right? It compresses. So if there is less of a difference between condenser and evaporative pressure, then it's not going to have to compress, which as it compresses, it uses energy, and energy costs money. So if we want to keep it efficient, we keep this lift low. And how do you achieve this though? Well, essentially what you want to do is have the lowest entering chilled water temperature, also known as chilled water return temperature. And by having that be lower, so you're having a lower entering water, the refrigerant and ultimately the compressor doesn't have to transfer as much heat from the water to cool the leaving water. Now, that's all well and good. Thing is in the real world, oftentimes we are running our, how do I say this? We're running our chillers hard typically, especially in the climates that really need chilling. And so maximizing lift, you could do it. It's just not something I would beat yourself over the head on. Now, load is something you definitely need to understand, because this is our staging parameter typically for switching and bringing on a secondary chiller, for bringing on a pony chiller, etc. And load essentially is a percentage representation of the performance of the chiller. So it can be calculated manually, but most of the time it's like FLA, full load amps, or it's a tonnage calculation based on temperature and GPM, so temperature delta and GPM, and versus the tonnage capacity, so that's hence your load. And what will happen is these things, right, these calculations will then be fed to your building automation system, which then, based on set points, will make determinations of bringing on the lag chiller to back up the lead chiller, or bringing on a pony chiller, et cetera, just based on your sequencing. Now, that is known as staging, and typically our stage parameters are somewhere like 90 to 95% load or full load amps, and you'll bring a second chiller on, and then 30% or less is your stage down. That's our typical settings. Now we'll use these things called partial load chillers, which is typically a smaller tonnage chiller to handle these loads below 30%. Because if you look at an efficiency curve with a centrifugal chiller and you look in that 30% or lower load requirement, you'll start to see that the efficiency drops pretty low. And so what you want to do is you bring on a air-cooled chiller or something similar, and that air-cooled chiller or something similar has a better efficiency curve for those lower tonnage requirements. And so you'll run that, and that is a way of saving energy. And just, it also gives you, in my opinion, a greater degree of control, of granularity of control for temperature, so that you're not introducing or removing a ton of BTUs from spaces and actually subcooling areas, which can be very detrimental once you realize the effects of subcooling on humidity and how you can actually dry out air too much and just can cause issues. All right, so there we have it. That is kind of our introduction to chillers. And now let's start to look at the air-cooled chiller. And I do not think we are going to get through water-cooled chillers in this episode. I just don't see how we do it when we're already at 20 minutes long. So water-cooled chillers, let's recap right on a couple things. With water-cooled chillers, or air-cooled chillers, with any chiller, we want to really understand what we're doing when we're controlling these things. And I have this concept that I call the flow of the sequence. We really need to think about that. What is the purpose of our chiller? It's to chill water, right? It's to remove BTUs from the water stream and reject those BTUs either into the atmosphere or into the condenser side of your system. But in order to do that, we have a flow. We need to go and make sure that we have water flowing, that systems are enabled, that pumping's enabled. And so I have this sequence that I've used time and time again, and it's been really beneficial for me, and it's really helped me to make sure my chilled water sequences and programming operate pretty much optimally and are very easy to troubleshoot. It starts off with system enable. We want to enable our chilled water system, usually based on ambient conditions, sometimes based on a call for cooling. This is just a system enable. This is not chiller enable. This is not pump enable. It's system enable. It simply allows our logic to start controlling to enable chilled water systems. Now, if you followed my podcast for a while, or you've been through our BAS programming bootcamp, then you know I'm a big fan of state-based control. I believe that you should utilize state-based control, and you should have logic that is commanded based on state. So you should have a cooling enable state, a heating enable state, and your logic should do specific things based on the state it's in. This way, it's easier to troubleshoot because you know what state you're in, you know what things should be doing, and it keeps things from just being crazily intermixed and confusing. So our system enable is our state enable for chilled water. From that point, we move on to valve control, and this is where we're going to go and enable our valve, and then we go to pump control, flow status, chiller enable, and temperature control. I'm going to dive through each one of these in greater detail. So as I mentioned, system enable is typically brought about by either schedule, call for cooling or load, or outdoor air temperature. From there, we have our valve control. Now, this is optional, but it's not optional. So what I mean by that is some chillers will command their own valve. I'm highly hesitant to let chillers command their own valve, to command their own pumps. Maybe I'm just a control freak, but I like to have control of those. So once the chilled water system is enabled, the isolation valves on the chiller should be commanded open by your control system. This should be the first thing you do. From here, you want to turn on your pump, typically your primary pump. And unlike boilers, you typically don't have circulation pumps with chillers. You typically have a primary pump and a secondary pump. And secondary pump is hit or miss with air-cooled. You don't always have secondary pumps with air-cooled chillers. Usually you'll have primary pumps with constant volume pumps, and you'll have the appropriate valves at the air handlers to handle a constant volume water stream. So just like hot water, there's various pumping setups, and you want to make sure that you're controlling based on how that works. But most of the time with air-cooled, you're only going to have primary pumps, and they're usually going to be constant volume. So from here, we have flow status. Now, there's really two ways. There's internal flow sensors that automatically enable the chiller, or an external flow sensor that, once proven, will allow your control system to send an enable command to the chiller. You can obviously, or well, maybe not obviously, but you can probably guess which one I prefer. I prefer the external flow sensor. That way I know its proven status, and also, typically, the chiller has its own flow switch, so that's a secondary safety. I don't want to rely on that secondary safety. I want my primary, which is my flow switch or flow sensor, and it tells me when the pump's on. From there, right, I've got my isolation valves open. My pump is running and flow is proven. Now, there's typically three ways the chiller will enable. It'll either self-enable based on an internal flow switch. It will be enabled via a set of contacts, typically like a RIB U1C, or via some sort of network command. My personal stance is to use the RIB U1C and hardwire. It's easier to troubleshoot. You eliminate the variable of networks, and you eliminate the variable of, is the controller inside the chiller working? By having a RIB U1C and some dry contacts, you directly know whether or not you are commanding that chiller to enable. From here, we move on to temperature control. Now, temperature control is pretty much the same for air-cooled as it is for chilled water or water-cooled, in that we either have an internal set point that's configured during startup or via some touchscreen display, or we have a control voltage being set to a set of contacts via a remote BAS controller, typically 0 to 10 volts, and doing a 10-degree reset. That's typically what will happen. Or we have a network set point command, usually via BACnet or LAN card. Now, as you know, I prefer hardwired. Look, I'm the first person to integrate things. I love integration. It's fun to me. It's exciting. However, when it comes to critical systems and I have an option to hardwire, I'm going to utilize that option. Now, that doesn't mean that you can't have a BACnet card for secondary monitoring. But my primary source of control I like to have be hardwired. I tend to find that from a troubleshooting perspective, as well as from just a peace of mind and stability perspective, hardwired wins the day. So from here, we're going to move on to our air-cooled chiller sequence of operations, and then I think we'll be done with this episode. All right, so in this sequence of operations, our air-cooled liquid chiller and chilled water pump make up this chilled water system. Now, it's in operation year-round in this sequence because maybe they're handling some process loads in an IDF or an MDF, and they just want to have that chilled water. And this chiller, the pump, is running constantly. Now, via some sort of chilled water flow switch, which is not really clear in this sequence, the chiller is enabled to operate. Via its own microprocess controls, the chiller is going to operate to maintain a leaving chilled water temperature of 55 degrees adjustable, which, man, that is really high. So that tells me this is most likely dealing with some sort of process load, because 55 degrees, I ideally would not want that controlling spaces and things that have tremendous heat loads. I would be looking more for 42 degrees, but that's just me. All right, so the chilled water leaving temperature of 55 degrees, adjustable, the pressure. Then there's some pressure control because this is a constant volume pump, and talks about the chilled water two-way valve bypass is located across the chilled water supply and return lines at the end of the main, and is essentially, it's acting as a way of balancing the pressure in the piping since we're using constant volume piping. So that's something you'll see sometimes, and it's something we'll cover in a future episode when we talk about pumping, piping, decouplers, bypass valves, mixing valves, etc. But there you have it, folks, right? That is air-cooled chillers. Now, I know we didn't get to water-cooled chillers, and we didn't get to multi-chiller control because I wanted to keep this episode under 30 minutes, as always. but we will get to it in the following week's episode. So I look forward to hearing your thoughts, questions. Definitely, if this stuff is confusing you and you're like, man, I just don't get this HVAC stuff, it's still a little muddy to me, I can't encourage you enough to pick up a copy of our Control Sequence Fundamentals course. It will be a game changer to your building automation career. It is invaluable to you. And maybe you've got a team of folks and you're like, man, my team of people really need to understand controls. I encourage you to reach out to us. We provide skill assessments that are completely online that will tell you exactly what you need to teach, or that we can teach your people to make them their most efficient selves. That way they're generating cash for you, they're happy, they're feeling fulfilled, and they're able to do more complex work that keeps your customers satisfied. So definitely reach out to us about that. And you can learn more about all of this by going to buildingautomationmonthly.com/188. Once again, that is buildingautomationmonthly.com/188. Thanks a ton. I look forward to talking to you all again next week. Take care.